The next topic we want to discuss in data structure is recursion. In order to understand recursion, we would start with this mathematical induction formula. You have probably learned this in high school. To prove 1 plus 2 plus 3 until n will equal to n multiply n plus 1 divided by 2. To prove this, we need to use mathematical induction approach. What this is trying to do is basically we assume that for some simple cases, P1, P2, they would stand the equation. So say n equal to 1, 1 will equal to 1 multiply 1 plus 1 will equal to 2 divided by 2, which is equal to 1. So they would be able to prove when n equal to 1, it is true, n equal to 2 is also true. Now, we need to use our induction hypothesis, assuming that pk is true. And based on that, we try to prove that pk plus 1 is also true. And that is the approach, what we call the induction steps. So, what is that related to recursion or computer science? So basically, what recursion is using the similar concept. A recursion function is basically a function that either directly or indirectly makes a call to itself. So now the question is, we can understand directly. So function 1, inside of the function 1 is calling function 1 again. So that is what we call a directly function call. But the question is, what does it mean indirectly? What this indirectly function call is like this one. You have a function 1, inside of the function 1 it calls function 2. So it's not directly calls itself. However, in function 2, somewhere inside of the function 2 is also calling function 1. So that you call another function which would call your own function. That's what we call indirect function call. So whenever that kind of thing is happening, it is considered as a recursive function. So we need to, since the function is calling itself, in order to prevent causing a infinite loop, things like. So basically what we call in this recursion is like an infinite recursion. We need to make sure that it will keep calling itself until a certain stage that you will stop. Just like our loop. The loop will give you a loop condition. So basically it will keep looping until the loop condition is false. Finding a recursive function. A recursive function is a problem must be written carefully because you are making a function calls itself. You need to guarantee that it will stop at some point. So the idea for each successive recursive function call is try to bring you closer to a situation that it does not need to call itself anymore. That is what we call a base case. Otherwise, if the recursive function is calling itself, that's what we call a general case. So there are two important cases that you need to pay a lot of attention when you are writing the recursive function. So this is the base structure, like a backbone of a recursive function call. So in a recursive function call, there is an if statement saying that if it is easy solvable condition, then we don't need to call ourselves anymore. Otherwise, so the if else part, otherwise you will try to recursively call the function itself, and then we will keep repeating this recursive function until we hit the base case. And therefore, in the previous slide, it says that whenever you try to recursively call yourself, you need to bring you closer to the base case scenario so that you can stop calling the recursive function call. This is a very simple example to describe that, and let's try to study this. Say now we create a function called s, and then it takes one parameter, and then based on this parameter, if n equals to 1, which is our base case scenario, then we just simply return 1. Otherwise, if n is not equal to 1, what we're going to do is that we return the same function s of n minus 1. So you can see that the n will keep reducing when it hits n equals to 1, so that you will have a base case, and therefore you don't need to recursive call yourself anymore. And then this is not the end of it. You will call return s n minus 1 plus n over here. So let's take a look of how does this work. So the function is given in the outline over here. Say now we call n equal to 4. So say in the main function, we call s of 4. So what's happening is that when s of 4 is called, you will come to the function, try to understand that since n is not equal to 1, you will go to this line, the recursive function call. So you will do return s, since n is 4, we will do n minus 1, which will end up with s of 3 plus n, which is 4 over here. So we will call this function. Since we see the return function immediately when the program or the compiler sees s of 3, it will stop executing the plus 4, but it will do is that it will call the same function at this time, n equal to 3. So when that is happening, we will stop the function over here, comes to the recursive function call, try to see that n is not equal to 3. So we will return s of 2, which is n minus 1, 3 minus 1 plus 3. So again, when this is C, immediately it will call the recursive function n equals to 2, and it will call the function, it's not the base case, is still a general case, so you will see that n is 2, so we will call s of 1 plus 2. So again, when s of 1 is C, it will call the recursive function. This time, we hit the base case because n is equal to 1, so we will simply return 1 over here. When this 1 is returned, go back to where that caused it. It will then continue the plus 2. So you see that it will end up with 1 plus 2 equal to 3, and we will be able to return this 3 to the place that caused it. So that we will have a 3 plus 3 equals to 6, return to the place that caused it. So we will end up with 6 plus 4 equals to 10. At this moment, you may be curious, what is this function trying to do? So basically, this function is the equation that we try to solve in the beginning of the slide. When n equals to 4, you will end up with 1 plus 2 plus 3 plus 4. That's what this recursive function trying to do. You may wonder, why do we write this recursive function? Isn't that a for loop is sufficient and much more straightforward? The truth is, yes, they are the same. Basically, it can easily write, it's probably even easier for you now since you already passed CS1 and CS2. Write a for loop to calculate that is actually easier. The only thing is that recursive function call is more powerful in certain circumstances, especially when the data structure is defined through a recursive approach. We've learned this. A tree structure is actually much easier to write a recursive function call to do the traversal problem. Compare with the one that we studied using stack and queue to perform different traversal problems. And we will see those slides as I promised you guys. So the key thing to understand here is that for every single recursive function, there is a corresponding loop function. They are equal to each other. Some of them are easier to write or understand. Some of them will requires more knowledge to understand it. Just like this one. This one is a little bit more complicated than a straightforward way to understand the loop. However, there are many different things that we will be able to discuss. Right now, I'm just simply show you a very simple-minded recursive function to show you what is a base case and what is a general case. If you read this code carefully, you will see that there are some actually problems or traps that will end up with an infinite recursive function. Here are two examples that you may want to understand. First of all, you see that this code, we assume users will provide, or the parameter will be provided as a positive value. What if, think about this n is given as -1. This loop or this recursion will never end because you will keep calling yourself and you will never hit n equals to 1, and therefore it will end up with an infinite recursive. On top of that, the int value as the parameters or the return value, it may end up with too big to fit in the integer. And there's another possibility is that this function will fail. So those are the detailed things you need to pay extra attention to when you are writing a recursive function. If we change this plus sign into a multiply, it will end up with a factorial function so that you will be able to recalculating the factorial values when n that is you provided. Of course, this gives you another warning or red flag that when you are writing a recursive function, you need to pay extra attention. N previously has to be less or equal to 0 at the beginning. At this time, n cannot be 0 anymore, because if we have an n comes into the factorial value, then you multiply everything with 0, will end up with 0. The return value might be even easier to go over the integer. So those are extra things you need to pay attention to. When a function called, basically, we need to stop the current operation and then jump to another piece of code. So a transfer of control occurs from the calling block to the code of the function. And basically, you also not only you need to jump to another location, you also need to remember where is the returning address, so that once that function call is done, you will know where to come back. When any function is called, this is something we discussed in the beginning of the semester. A runtime stack is used to keep track of all of the important information, including parameters, including local variables, return addresses, and all kind of things that's going to make the function work, so that we will have a runtime stack that stores the activation record. So activation record contains the returning address, including the parameter, local variable, and space for the function's return value, etc. So a lot of things need to be kept track of. The activation record for a particular function call is popped off the runtime stack when the final closing brace in the function call is reached. So when that function is done, we will be able to pop it away and then move to the next level one. And of course, since this is stack, last in first out is the order that we will going to operate. So at this time, when a function returns value, if not void, is brought back to the calling block returning address for use there. So you can see that the examples that we see when we call SL4, this is the ideas of the runtime stack. Inside of the main function, since we call SL4, we will go to SL4, and when SL4 is called, we will call SL3, which is n-1, and then we will call SL2, and then we will call SL1. So when SL1 is a base case scenario, we will be able to remove it, pop it away, and come back to SL2, come back to SL3, come back to SL4. When SL4 finally generates a value, it will return back to the main function, and then that's going to be the end of this recursive function call. Let's take a look of another example. This time, we use two parameters. So this is like the next level of the simple-minded recursive function call that we have seen. So saying that in this recursive function, we initiate result equal to 0. We take two parameters. If b is equal to 0, so we will say result equal to 0. Obviously, this is our base case scenario. Otherwise, as long as b is greater than 0, then what we will do is we will have a, which is the value plus function call of a, the same value of a, and now we do b minus 1, so that we have 1 minus of the b. Hopefully it will reach to b equal to 0, and we will end with the recursive function call.